Hello, everyone. Today, we're diving deep into the very heart of the periodic table, the D and F block elements. We often see them as just that big block in the middle, but they are so much more. They're practically the backbone of our modern world, responsible for everything from the strength of our tallest buildings to the amazing colors in an artist's paint box.
Think about it for a second. In school, we learn all about the superreactive metals on the left side and the nonmetals on the right. But what about that huge territory right in the center? What's their story? Well, today we're going to find out what makes them so incredibly unique.
So, here's how we're going to do it. First, we'll get introduced to the D-block elements. Then, we'll figure out what that whole transition label is all about. After that, we'll explore their, let's say, colorful personalities. Then we'll take a peek at their cousins in the F-block. And finally, we'll see why all of this matters in our everyday lives.
All right, let's jump right in. Our main focus today, the D-block elements, are sitting right there in the middle of the periodic table, nestled perfectly between the S and P blocks.
The real secret to understanding them is all in their electron configuration. See, unlike the other elements, as you go across the D block, the electrons are filling up the D orbitals of the second-to-last energy level. It's this slightly weird filling pattern that is the key to all their unique chemistry.
Let's take a closer look at the first row here, the 3D series. As you go from scandium all the way to zinc, you can see that 3D orbital filling up, one electron at a time. But wait a minute. Take a really close look at chromium and copper. See anything a bit strange?
Exactly. They don't quite follow the rules you might expect. Instead of having 2 electrons in their outer 4s orbital, they just have 1. So what's going on here? Well, it all comes down to one powerful drive, the atom's desire for stability.
This slide shows a really fundamental idea in chemistry. Atoms just want to be stable. And it turns out that having a D orbital that's exactly half full, like in chromium, or one that's completely full, like in copper, is an especially stable and balanced arrangement. This balanced state is so energetically favorable that an electron will actually hop over from the 4s orbital just to achieve it. It's pretty cool.
Okay, so we know where they live and a little about their electron secrets. But why are they called transition metals? The name originally came about because their properties seem to transition between the metals and the nonmetals. But today, the official definition is way more specific.
And here it is. The key to being a true transition metal is having a partially filled d orbital at some point, either as a regular atom or when it becomes an ion. And this strict rule actually leads to some surprising exceptions.
This definition really makes you think, doesn't it? Let's take zinc again. As a neutral atom, its d orbital is totally full. When it forms its most common ion, Zn2+, it loses its 2 4s electrons, but that d orbital is still full. So, going by the official rulebook, does it count?
And the answer, if we're being super technical, is no. Zinc, cadmium, and mercury always have a full D subshell. But since they mark the end of each transition series and their chemistry is so closely related, it just makes sense to study them all together as one big family.
Now for the really fun part. Those partially filled d orbitals we've been talking about, they're the reason for some of the most fascinating and beautiful properties that you'll find anywhere on the periodic table.
Just look at these colors. This is not some kind of trick. These are actual solutions with different transition metal ions. From the lovely purple of vanadium to that deep, rich blue of copper, their colors are just iconic. And guess what? There's a very precise electronic reason for all this beauty.
It's all because of something called a d-d transition. In these ions, the d orbitals split into slightly different energy levels. So when light shines through, an electron can absorb a very specific color of light to jump up to a higher level. The color our eyes see is simply all the light that wasn't absorbed, the complementary color. It's such a beautiful consequence of their unique structure.
But their vibrant color is just the beginning. Because they can lose a different number of d electrons, they can have multiple oxidation states, like iron forming both Fe2+ and Fe3+. They also form these amazing, complex compounds, are often magnetic, are incredible catalysts for chemical reactions, and they make super strong alloys. They're basically the Swiss Army knives of the periodic table.
All right, let's quickly shift our focus to the F-block elements. Those 2 rows that are usually kept at the bottom of the periodic table. They're often called the inner transition metals. One of the most important ideas here is something called the lanthanoid contraction. As you move across this series, the nucleus gets more and more positive, pulling all the electrons closer. But the 4 F electrons that are being added are terrible at shielding the outer electrons from this strong pull. And the result? the atoms actually shrink as you go across the row. This has huge consequences for the elements that come after them, by the way. It's the reason hafnium is almost the exact same size as zirconium, making them super difficult to separate. And this comparison chart really shows the difference between the two F-block series. The lanthanoids are mostly stable, they usually have a +3 oxidation state, and they're crucial for things like the powerful magnets in your phone. The actinoids, on the other hand, are all radioactive, their chemistry is much more complex, and they're pretty much defined by their role in nuclear technology.
So, we've gone through a lot of the science, but how does this all connect to our lives? Let's bring it back to the real world, because these elements are quite literally all around us.
Honestly, it is impossible to overstate just how important iron is. As the main ingredient in steel, it is the skeleton of our entire civilization. It's in our buildings, our bridges, our cars. It's without a doubt the most important construction material in the world.
And just think about the history of money. The coinage metals, that's copper, silver, and gold, they were the foundation of currency for thousands of years. Their durability and value basically created the rules of trade long before we ever understood their atoms. And their role as industrial workhorses is just as vital. Many of these metals are amazing catalysts. They provide a special surface where reactions can happen much faster and with less energy, allowing us to efficiently produce everything from the fertilizers that feed billions of people to the plastics in our homes.
And we absolutely can't forget the F-block. The incredible amount of energy packed inside the nucleus of elements like uranium is what we harness in nuclear power plants to provide electricity for millions around the world.
When you put it all together, what really defines these elements is their sheer versatility. From the steel in a skyscraper, to the color in a beautiful painting, to the catalyst that makes a life-saving medicine possible, the D and F block elements are absolutely central to our world. It really makes you wonder, what new amazing things will this versatile middle kingdom of the periodic table help us discover next?